Alright, welcome back everybody. In this video we're going to talk about the Fundamental Theorem of Calculus Part 2. Now up until this point in time we've looked at a few different ways to find the values of definite integrals. We looked at using the limit of a Riemann sum with an infinite number of rectangles to find the value of a definite integral. We looked at using areas and estimating based off of geometric area formulas. We looked at finding the definite integral of a constant function. We looked at using the numerical integral feature on our calculator to find the integral of a function. Finally, today, with the Fundamental Theorem of Calculus Part 2, we're going to look at how to actually find the value of a definite integral algebraically. And you see here on the screen the Fundamental Theorem of Calculus Part 2. If we have a continuous function, and if capital F is any antiderivative of the function, then in order to find the integral from a to b of f of x dx, we take the antiderivative evaluated at b minus the antiderivative evaluated at a. So in short, in order to find the value of a definite integral, what we're going to do is we're going to find the antiderivative, or an antiderivative, of the integrand, and it can be any of them, and we're going to opt to use the one with a constant value of 0, but we're going to find any antiderivative and then evaluate it at the two limits of integration. So let's go ahead and see this in practice. We'll go on down here to example number 1. We're going to find an exact value for the integral from 0 to 3 of the quantity 3x squared plus x minus 2. So in order to find this integral, what I'm going to do is I'm going to find the antiderivative of 3x squared plus x minus 2. The antiderivative of 3x squared is x to the third. The antiderivative of x is 1/2 x squared. And, excuse me, the antiderivative of 2 minus 2 is going to be minus 2x. So there's our antiderivative, and this is kind of what the notation should look like. We're going to evaluate this from 0 to 3. So what I'm going to do is I'm going to substitute 3 in here for x, everywhere where there's an x. And I'm going to subtract away what I get when I substitute 0 in here for x. And then I'm going to calculate the values of these, and that's going to give me my definite integral. So I've got 27 plus 9/2 minus 6 minus 0 plus 0 minus 0. And doing all the calculations here, I end up with 51 over 2 minus 0. And the value of my definite integral is going to be 51 over 2, or if you prefer decimals, 25.5. And that's how we use the Fundamental Theorem of Calculus Part 2 to find a definite integral. We take the antiderivative, and then we evaluate it at the limits of integration, taking it evaluated at the upper limit of integration, minus it evaluated at the lower limit of integration, and that gives us the value of our definite integral. All right, let's look at a few more examples just to get this, under our belts a little bit. In example 2, part A, the integral from 0 to 1 of x squared plus the square root of x from 0 to 1. So first I'm going to find my antiderivative. The antiderivative of x squared is 1/3 x cubed. And the antiderivative of the square root of x, let's see, that's x to the 1/2. So I go up 1 power. That's going to end up being 2/3 x to the 3/2. And I'm going to evaluate this from 0 to 1. Alright, so I've got 1/3 times 1 cubed plus 2/3 times 1 to the 3/2 minus 1/3 times 0 cubed plus 2/3 times 0 to the 3/2. And now I do my calculations. This ends up being 1/3 plus 2/3. And the second ends up being 0 plus 0. And so we end up with 1 minus 0, or 1, for the value of this integral. Now just to double check, we already know how to find integrals numerically on our calculator, so I'm going to just double check here, make sure we've done everything right. My numerical integral of x squared plus square root of x with respect to x, 0, 1. This should be 1. And it is. We've got some garbage digits because of the graphing calculator algorithm, but when we see those garbage digits at the end, we know that this is trying to tell us that it's actually 1. Alright, on to example B. The integral from negative pi over 3 to pi over 3 of 4 secant of theta tangent of theta d theta. So we find the antiderivative first. What do we take the derivative of in order to get 4 secant of theta tangent of theta? And that is going to be 4 secant theta, which we're going to evaluate from negative pi over 3 to pi over 3. So we've got 4 secant of pi over 3 minus 4 secant of negative pi over 3. You remember back in pre-calculus when you did all those circle charts with the values of the various trig functions. Here's where knowing those circle charts really comes in handy for us. We want to know the secant of pi over 3. And let's see, the secant of pi over 3 is 1 over the cosine of pi over 3. The cosine of pi over 3 is 1/2. So the secant of pi over 3 is going to be 2. And the secant of negative pi over 3 is going to be the same. It's going to be 2. And so our value here for the definite integral should be 0. Alright, go back, double check. We've got the integral of 4 secant times tangent with respect to x from negative pi over 3 to pi over 3, and we end up with 0. So I feel pretty good about what we're doing here. I'm going to stop checking my answers with the numerical integral and just get into finding them now. Here we go. Part C. The integral from 0 to 2 of 3 to the x times the natural logarithm of 3. We need to find the antiderivative of this. Again, it's going to be really important here for us to be really confident with our basic derivative rules in order to find these derivatives quickly and easily, or these antiderivatives quickly and easily. What do I take the derivative of to get 3 to the x times the natural logarithm of 3? The answer to that question is 3 to the x. And then I'm going to evaluate that from 0 to 2. So this is going to be 3 to the second minus 3 to the 0, which is 9 minus 1. And so the value of this definite integral should be 8. Alright, part D. find the antiderivative. The antiderivative of x to the 1/3 is going to be 3/4 x to the 4/3. And the antiderivative of minus x is going to be minus 1/2 x squared. And we're going to evaluate that from -1 to 8. So we've got 3/4 times 8 to the 4/3 minus 1/2 times 8 squared minus 3/4 times -1 to the 4/3 minus 1/2 times -1 squared. And we'll calculate all these values. 8 to the 4/3 is 16. And 8 squared is 64. And -1 to the 4/3 is 1. So 3/4 times 1. And -1 squared is also 1. And so we've got 12 minus 32 minus the quantity 3/4 minus 1/2. And so we've got -20 minus 1/4. That's going to be -81 over 4. Or for those of you who like decimals, -20.25. Alright, so we're going to call it quits on this video. We're going to come back in a second video here to look at the remainder of example 2. See you guys then. Have a great rest of your day.